All right, so we are doing some suck because I'm loud and that thing's right there. Okay, but we are going to continue what we were talking about with graphing. Okay, but this time we are connecting the original function with the first derivative, second derivative, et cetera, et cetera. But basically now instead of taking the function like the actual equation, you're going to be given a graph. Okay, and you might be asked to graph the derivative or graph the second derivative, or you might be given the second derivative and you have to graph the original or the first derivative. And basically what you have to do is you have to use your knowledge of what the first derivative does, what the second derivative does, so that way you can graph. That's why I have that list over there on that side board, so you can use that as a reference. Okay? So let's just jump right on into it. Looking at the notes, the back side of the notes, okay? It says, given the graph shown, this is the graph of f. So this is the graph of the original function, okay? We have to sketch the graph of f prime and f double prime. Now, one of the features when it does come down to graphing is, think about it. This right here is an example of what? This a quadratic, right? And aren't quadratics using the form of x squared? So when you take the derivative of x squared, what do you get? 2x. And 2x is an example of what type of function? It's a linear. So basically, our first derivative graph should look like a linear function, should look like a line, okay? And when we take the derivative again, we get what? 2. What does the graph of 2 look like? Just a straight line, so a constant. So knowing that can help guide us when it comes down to graphing these functions, okay? And say instead that this was the graph of the derivative. So then the original function would be a what? What's one before a quadratic? A cubic. So then using that can also help, okay? But one of the main things is you have to, knowing that, you just can't draw a random line, okay? You got to be careful. Now, if you look at this graph here, we have a min, don't we? Okay? Minimums are called extrema, right?
Yes.
And if there is a minimum, right, that means the graph is the graph is going from negative to positive, is it not?
Yeah.
Okay? So that basically means that on our derivative, we should be going from negative to positive. Negative to positive. So in order to go from negative to positive, that means we have to probably be crossing over the x-axis, are we not? Wherever there's an extrema, that is where we have, that's where we have an x-intercept. Okay? Anytime we have an extrema on our original function, that meant that, hey, the first derivative, when we set it equal to 0, we made our number line, we went from negative to positive. So that means that on our derivative, we were equal to 0. Does everybody understand that? And because it's a minimum, that means that on our number line, if we were to draw it out, right? So at 1, that means we were going from negative to positive. And that's exactly what we need to do on our derivative. We need to go from negative, cross over the x-intercept, and go up to positive. So this is our derivative. That's not my best line. I'm trying this new program, like I said, so. But that is your derivative. Any questions on how?
So you don't need to know anything specific, you just need to know what the x-intercept is?
Exactly. And the only reason why you don't need to know like where exactly it crosses the y-axis, as you notice on your notes, there's no y-axis labels given. This one, clearly I pulled this from the internet so that I could have a picture to use, but they're never going to have any of this because there's no way to tell from the graph just by itself where exactly you're going to be crossing the y-axis because you don't have the function. Okay? So it's more concerned about where exactly is it going to cross the x-axis because we know we have an extrema. So anytime we have an extrema on the original function, we have an x-intercept on the derivative. And vice versa. Anytime we have an x-intercept on the derivative, we're going to have an extrema on the original. Okay? Now, the second derivative. I'll do that in different color. Go blue. So what we can do is we can look at the original graph. Remember, second derivative associated with what? Talks about concavity. Now, if we look at this graph right here, this graph is going to be concave the entire time, right? Negative infinity to positive infinity. If it's concave up, then that means that the second derivative is greater than 0, which means that it does need to be that constant line that's going to be above your x-axis. Now, where you put it, it really doesn't matter. That's why your y-axis isn't labeled. And again, we can't really tell because we don't have the equation where exactly this graph is going to be crossing the y-axis. But we do know it needs to be above the x-axis. Questions? Okay, so let's recap. Wherever there's an extrema on your original function, there is a what on your derivative? An x-intercept. Okay? Whenever the graph is decreasing, that means that, so look at the black line. Whenever that graph was decreasing, that means our derivative was what? It's negative, below the x-axis. Whenever it was increasing, it was positive, above the x-axis. Okay? And then let's talk about the blue line. Since it was concave up, that meant that the second derivative had to be greater than 0. That's why we drew this constant line above the x-axis. It was concave up the entire time. So at no point in time would it ever go to be below because it wasn't concave down at any time. Make sense? Let's look at another one. It's the same graph, but this time, this graph represents the derivative. Okay, this graph represents the derivative. You got to tackle it a little bit differently. You have to think backwards. Okay? So, let's graph. What do you want to graph first? Do you want to graph the original or the second derivative? Okay, we'll graph the original. Okay, we'll do this in red, green. Okay. So, think about it. This is the graph of the derivative. Okay? The derivative tells us where the original graph is increasing. It tells us where there's a max or a min. Excuse me. Those are two things that the derivative tells us. Okay? So if the derivative is positive, right? And we're not talking about the slope. We're talking about where it's positive, where the derivative is positive. That means that on the graph of the original, it's what? It's increasing, yes? Is it not? Where the derivative is positive, the original graph is increasing. Where it's negative, the original function is what? Decreasing. And where it's positive, it's what? It's increasing. So you can kind of have a little bit in your mind, okay? I wish I could do this without this thing like writing on it, but this is touchscreen. So if anything, can't even draw on it either. I'm just going to do this in a completely light color, okay? We're going to know that basically I should be increasing, decreasing, and increasing. That's what my graph should look like. Doesn't that look like a cubic? Okay, so now it's more of a matter of, okay, where are my maxes and my mins? Because it's going to have to change, right? It's going to have to go from positive to negative. There has to be a maximum somewhere. Negative to positive, there's got to be a minimum somewhere. Where do you think those are going to be? Exactly. Remember what I said, wherever there's an extrema on the original, there's an x-intercept on the derivative? So wherever there's an x-intercept on the derivative, there's an extrema. So that means at -1, if we're going from positive to negative, we should have a what? Don't think concavity. We should have a max. So we're going to have a max at -1. Now, if you're asking, well, why did you draw it up there? Well, like I said, we really don't know exactly where these maxes and mins are lying, but we do know that at -1, we need to have a max, okay? You could have drawn it down here as long as you're increasing going to that max. Where's my min going to be? At 3, the other intercept, okay? I'm going to have a min there. All right? So I'm going to be increasing until -1, decreasing into 3, and then increasing afterwards. Because I was above the x-axis, I was positive on my derivative until -1. I was negative between -1 and 3, and then I was positive after 3. And that's the graph of our original function. Questions? Okay. No questions? All right. So let's grab the second derivative. Okay. Second derivative. Clearly, since our first derivative is quadratic, our second derivative should be a what? It should be a line, right? And it's, the way I look at it is I treat my first derivative like my original function. Because isn't the second derivative just the first derivative of the first derivative? Okay, so I'm just going to treat my first derivative like the original function. Wherever there's an extrema, there's a what on my derivative? X-intercept. So that means that it's going to have an x-intercept. Okay, there we go. Have an x-intercept at +1. Since this is decreasing, it should be negative, and where it's increasing, it should be. And there's my second derivative. For anyone watching this video, please apologize for the sloppiness. I'm checking out a new system. I don't like it. That's why the pictures are so ugly and my handwriting is so ugly. Okay. All right, so looking at this worksheet that I handed out, we're looking at number 1. Okay, this is the graph of the original function, so we need to sketch the derivative and the second derivative. Since this is a cubic, our first derivative should be a quadratic, and then our second derivative should be a linear function, a line. Okay, so remember, wherever there is an extrema on your original, there is a what on your derivative? X-intercept. So you got an x-intercept, not there, but somewhere like right there in between 0 and -1. And then you have another x-intercept at, what about 2? Okay, calibration's a little bit off on this, but that's okay. And so then if the graph is going up on the original, increasing, then on the derivative we're what? We're positive. Wherever it is decreasing, it's what? Negative. And then, oh, Jesus, this sucks. All right, and then it's what? And then it's increasing. It's positive. Okay? So you really don't have to worry about how low that little hump goes. You really don't have to worry about it, okay, as long as it's there. All right, and then for your second derivative, it should look like a line. We know that second derivative deals with concavity. Where's the graph concave down? From where to where, you say? From -infinity to where? What would you say is that inflection point on that original graph? At about 1? Okay, so we have an inflection point right there at about 1, which means that if there's an inflection point and it is changing from being concave down to concave up, that means on your second derivative, where there's an inflection point, there is an x-intercept. I'm having the same problems I had with a regular pen on this thing. Okay? Because remember, inflection points, that's when it equals 0 and it changes signs. Okay? So it changes signs. We're going from concave up to concave down. So we have an inflection point there. And since it's concave down, that means we're below the x-axis, we're negative. Concave up, we're positive. There's your second derivative. So second derivative is in green. How we do? Good? Okay. Do number 2, and only number 2, and I'll check back in. How we do? Good. Okay. Our original function looked like a what? What did our original function look like?
Oh wait, our original
It's a four thing. Give me the shape. What did it look like?
It looks like an upside down W. Or like an M.
Like an M.
Like an
It looks like an M. There we go. Okay. So remember, wherever there's an x-intercept on your derivative, there is a extrema. So there's an x-intercept in -2. Is that a min or is it a max? It is a max because we're going from positive to negative. Okay. And then where's my next one? It's 0. Is that a min or a max? Min, because I'm going negative to positive, below to above the x-axis. And then where's my next one? 2. Is that a max or a min? It's a max. Okay. That's supposed to be a 2. And so then wherever it's positive, we are what on the original? Increasing. Wherever it's negative, we are. And then wherever it's positive, and then wherever it's negative, we are. So this is a really poorly drawn one, but it should, as long as we have our extreme in the right place, we're good to go. They don't have to be necessarily even. One could have been higher than the other, like mine kind of is. So as long as you have them in the right place. Questions on that?
So maybe it's like increasing and decreasing the derivative?
No. When I say increasing, I'm talking about the original graph. Because wherever the first derivative is positive, that means we're increasing on our original. So that's why I said we're increasing because we're positive on the derivative. We're decreasing on the original because we're negative on the derivative, and so on and so forth. Now for the second derivative, it should look like a what? A quadratic that is actually is upside down. Okay, and then if we use our first derivative like our original, then that means we should have some x-intercepts with this quadratic, shouldn't we? Where are the x-intercepts? -1 and where? +1. And since it is a quadratic that's opening down, we can look to see, hey, we're decreasing, so we're below, increasing above, decreasing below. So go. If you drew your maximum a little higher, that's fine. It's more about where the x-intercepts are because that's the information we have. That's what's given to us. So we use those to graph our function. Questions? Okay, well, let's look at number 3. Same thing. Do 3 on your own, and I'll double check you. All right, so take a look at this one. Okay. We know that this is the second derivative. The second derivative talks about what? What's the second derivative talk about? Inflection points as well as concavity. So remember, if the second derivative is less than 0, meaning that if it's negative, like it is here from -50 to -3, that means it's going to be what on the original? I'll say it again. If the second derivative is negative.
Teachers, please.
So since the second derivative is negative, that means we're going to be concave down up until we get to -3. At -3, there's going to be a point of inflection, okay? Because we have an x-intercept on our second derivative, that's going to be a point of inflection. After that, since the second derivative is positive, we're going to be concave up all the way up until 2, when we're going to change our concavity again. Okay, so we're going to be concave up all the way to 2, and then we're going to change our concavity again at 2, and then we're going to be concave down the rest of the way. Okay, so it forms like a little M, and that's the graph of our original function. Now on our derivative, if we use the second derivative to help us, and we want to use what we're basically given. That's why I'm always referring back to what's given to us. So since this is the second derivative, I'm going to treat that basically like the derivative of the first, which it essentially is. Which means that wherever there's an x-intercept, that means there's going to be an extrema on your the function before it. So that means that at -3, there's actually going to be an extrema, and because we're going from negative to positive, it's going to be a min at -3, And because we're going from positive to negative at 2, we're going to have a max. So this is going to look like so. And that's the graph of your first derivative. So it's going to come with practice, but that is okay. We will get the practice in before your quiz. It's going to be on Friday. So just make sure that you guys do your homework. The ones that are starred, you can use a calculator, but really all you need to use the calculator for is to it's just to graph the intercepts. Everything else can be done using derivatives, okay? So if you guys have any questions, of course, you can always message me over the weekend. And you guys have a good day.